Hi, I'm Barbara Andrews, and good AI agents can answer questions, but a great AI agent keeps getting smarter, faster, and more reliable with every iteration. This session focuses on how to optimize and fine-tune AI agents once they're already running, so they continue to improve in production rather than stagnate or degrade over time. You'll learn how teams refine prompts, adjust model configurations, and apply systematic evaluation and monitoring signals to drive measurable improvements in response quality, cost, efficiency, and performance. The takeaway here is production AI isn't static. It's continuously tuned to better deliver results with every new insight. If your AI agent is producing answers that are almost right but not quite there, selecting the right optimization strategy can make a dramatic difference. We'll compare 3 approaches for improving model behavior. First, supervised fine-tuning. This strengthens consistency and correct phrasing by training the model on labeled examples. Reinforcement fine-tuning. This focuses on complex reasoning by iterating through prompts and scoring outputs with a grading function. Direct preference optimization refines response quality by teaching the system which answers are preferred versus less desirable ones. Consider a travel planning AI assistant recommending hiking routes. If the issue is formatting messy directions or incorrect terminology, supervised fine-tuning can enforce the correct structure. If the recommendations require step-by-step planning and decision-making, reinforcement training helps to optimize reasoning. If responses sound technically correct but need improved tone or clearer suggestions, performance-based tuning quickly teaches the model which style users prefer. A practical guiding principle is to match the tuning strategy to the problem type, structured accuracy, reasoning quality, or response preference. So optimization efforts directly target the behavior that most needs improvement. If you want a model to learn the right answers instead of guessing, the training model format must be precise. Structured message-based dataset format used for supervised fine-tuning is where the conversations are broken into ordered role content pairs, like system instructions, user queries, and assistant responses. The structure ensures the model sees exactly how a dialogue unfolds and what the expected outcome should look like. Consider a scenario involving an outdoor gear assistant that helps users understand product specs, and a training conversation asks about a jacket's waterproof rating, and the labeled responses demonstrate both a short answer and a more explanatory follow-up. The benefit is that the model learns consistent, context-aware responses that mirror successful examples. A strong operational guideline here is to prepare clean, clearly structured conversation records with correct roles and high-quality responses. Ensure the fine-tuning process receives reliable supervisory signals that improve the agent's accuracy and consistency. Want an agent that gets better at reasoning, not just parroting examples? Check out the training data shape for reinforcement fine-tuning, or RFT. At the top, you provide the messages that define the task context. A developer instruction like, "You are a trip planning assistant," plus a user request such as, "Plan a 3-day coastal hiking trip in Wales." Below that sits a reference block, here labeled Ideal Itinerary. That represents what good looks like. and a grader panel that scores the model's generated answer. It takes the model output as input and compares it to the reference. It applies an evaluation metric, shown here as fuzzy match, and produces a score. That score is the feedback loop to RFT, and it uses it to push the model toward higher quality, multi-step solutions. A practical scenario here is you're improving a trail itinerary agent, so it consistently produces safe, structured plans, days, mileage, campsites, weather constraints. And instead of labeling hundreds of perfect responses, you defined a grader that rewards outputs that match required structure and key constraints. The benefit here is you can iterate quickly and optimize complex planning behavior at scale. A smart guideline: keep the grader clear, repeatable, and aligned to your outcome that you care about, like structure and constraints. And validate the format early so every prompt has a matching reference plus scoring rule. Otherwise, the model will learn the wrong signal. If you want an AI system to learn what better actually looks like, preference-based training is a powerful lever. This slide shows the data structure for direct preference optimization, or DPO. You start with a prompt, then provide two candidate responses, one preferred and one not. And instead of prescribing the exact correct answer, the model learns by recognizing which response aligns better with expectations, helping refine tone, usefulness, and practical guidance. Picture a trail planning assistant advising hikers. By comparing a response that clearly explains safety preparations against another that is vague or poorly tailored, the system learns to favor more helpful, context-aware answers. The payoff is faster alignment of model behavior with real-world expectations. A helpful implementation principle is to craft preference pairs that clearly highlight meaningful differences in quality. Well-chosen contrasts provide a far stronger learning signal than subtle or ambiguous ones. Building a strong, fine-tuning data set starts with the right data strategy. You can rely on real interaction data when documented conversations or logs exist, generate synthetic examples when real samples are scarce or sensitive, or combine both in a hybrid approach. For example, using real data for common user scenarios and synthetic data for edge cases. Next, prepare your source materials. For synthetic generation, clean PDFs or markdown content can drive Q&A data sets, and open API specifications can help guide tool use examples. For real datasets, gather chat logs, support tickets, or historical interactions, and remove irrelevant formatting or marketing texts. Then generate or curate structured training examples, often as JSON-L records, either produced by tools like Foundry's Q&A or tool use generators, or by converting real conversations into structured prompts and responses. Before training, verify both format and example quality. Ensure JSON-L structure and role fields are correct. Review generated responses for accuracy, and begin with roughly 50 to 100 well-checked examples before expanding. Finally, measure outcomes after fine-tuning using validation datasets, benchmarks, and performance metrics. If results fall short, analyze which prompts fail and refine the dataset accordingly. Sometimes the model simply needs more cleaner, or more diverse examples to improve. Here's a practical scenario. A customer support assistant trained from product documentation and ticket logs can produce clearer troubleshooting guidance once high-quality examples and structured prompts are added. If a fine-tuned AI agent still misses details or responds inconsistently, the difference between mediocre and outstanding performance often comes down to training hyperparameters. This slide highlights 3 of the most influential knobs. Epochs control how many times the model learns from the dataset. Batch size determines how many examples it processes in each update. And the learning rate multiplier regulates how aggressively the model adjusts its weight. Small targeted changes to these parameters allow you to shape how quickly and effectively the model learns. Picture a customer support assistant learning from product documentation and conversation transcripts. Increasing epochs slightly may help it better internalize structured troubleshooting steps, while adjusting batch size improves training stability as the dataset grows. The advantage is more reliable answers without redesigning the entire dataset. In this demo, we're going to focus on optimizing an AI agent by choosing the right model, because model selection has a direct impact on quality, latency, cost, and reliability in production. You'll see how different models can dramatically change an agent's behavior, even when the prompts stay the same, and why bigger isn't always better. By aligning the model choice to the task at hand, such as reasoning depth, response speed, or cost constraints, you can deliver a better user experience while staying efficient at scale. This is critical for Gen AI Ops decision points and a key skill tested in AI-300, where optimization means making informed, measurable trade-offs, not guesswork. So in this demo, we're going to be answering a simple question, but an expensive question. Does this agent actually need a larger model? We use the chat playground to compare models using the same stabilized prompt and the same test inputs and make a production-ready decision about cost, latency, and quality. So we are back now in our chat playground to start off here. And so far, we've done 2 critical things in previous demos. First, we stabilized a prompt so that the agent behaves consistently. Second, we saw how small changes can slightly break that behavior. Now comes the question teams faced right from production. Should we upgrade to a bigger model, or is the same one already good enough? The smaller one, many teams guess. Here the demo shows how Microsoft Foundry Chat Playground lets us make that decision intentionally by comparing models before we deploy an agent or automate anything. Foundry explicitly supports model comparison and prompt engineering in the playground for this exact purpose. So should we upgrade to a bigger model or a smaller one? Is it already good enough? So this demo is not about picking the smartest model. It's about optimization, choosing the right sized model that meets the behavior contract we already validated. We won't change the prompt. We won't change the inputs. What we're going to do is we're going to change the model this time. That's a best practice for model comparison and pre-production decision making. So we're going to use one of the prompts that we used earlier in our instructions. It was actually very specific We may apply the changes here. Let me apply them. And what we're going to note is we're going to tell it you're an outdoor trail assistant for beginning hikers, and the response format will be one recommendation in one sentence, talk about why it matters, what to bring, what to watch for, and then give it some rules. So the response should be under 120 words. And we want it to be explicit about its uncertainty and to not invent trail or weather conditions. So those are the ground rules for it to use here. And now what we're going to do with this is we're going to stabilize the agent with a ready prompt right here. This is part of our behavior contract. So we care about protecting is optimizing this. And so what we're going to do is we're going to use the model right here that we've been using in previous demos. It's our GPT-5.4 mini. And we're going to run one of our prompts that we've run before. We should hopefully get back a pretty reasonable response given the instructions here. And so this is our base model as engineers. And what we're doing is we're looking for clear structure, safety-aware language, explicit uncertainty, and reasonable verbosity so that we can have the output here that we're looking for. So recommendations that it makes, it says it cannot judge this specific trail. So it's telling us what it can't do and then why it matters. Steep climbs are more listed here. And then also any other uncertainty that it finds, slippery footing, numb fingers, getting too cold, too fast. So it's telling us some things to watch out for. So it's telling us about uncertainty that works out well. But before we switch models, it's important to be explicit about what we're evaluating. We're not grading poetry here. We're checking, does the output follow the structure? Does it respect uncertainty? Does it avoid overconfidence? And is it concise enough to be usable at scale? So these are exactly the kinds of signals teams later monitor and automate. But we start by understanding them manually. So what we're going to do is we're going to switch over to a different model. And now this is the model that we can use right here. It's our GPT 5.4. So this model that we're going to compare this with, what we're going to do is we're going to compare some of the outputs live. And we'll note with this that we've changed only the model. And we're going to use that same prompt again. So let's have that steep trail here again. And let's see what it says for us. So same prompt again. Let's see the response. And we're going to match the two up with one another. And notice it tells us recommendations. Generally no. If you're a beginner for a steep trail in cold and windy weather, it's usually better safe for another day or replaced with an easier, more sheltered hike. And then why it matters, notice it says, I cannot judge your exact trail in Oregon. And so it's telling us its uncertainty. And then about the steep trail, it's harder when the wind increases, balance issues. So it's telling us a little bit about things that could happen here, why it matters, what to bring, warm layers. So it gives us a little bit of a different response. And you may see a charged phone, a map definitely here needed, a little bit more detail than what we saw earlier. Watch out for exposed ridges. So some different things it calls out of what to watch for. And we can compare these. And does the larger model add clarity? Do you think it adds nuance? Is it unnecessarily long and verbose? Did it change our safety posture? Do you think it improved reasoning in any meaningful way? So this is really the interesting part. Often the larger model sounds more confident, but it isn't always more useful. For this task, you need to ask yourself, did we gain enough value to justify higher cost and latency? That's what we got to think about. Did it work out for us? So this decision directly is going to affect production outcomes. It's going to affect the cost per request, the late response latency, the overall system reliability, and optimizing agents for production. Often means not using the largest model if a smaller one already satisfies the behavior contract. This aligns with Microsoft Azure Foundry here and encourages teams to experiment and compare models in the playground before deploying agents. So think of some of the best practices we saw here. First, stabilize the prompt before comparing. Second, change only one variable at a time. Third, evaluate behavior, not just how impressive the answer sounds. And finally, optimize for production needs, not theoretical capability. So this demo kind of shows us why optimization comes after prompt stabilization and regression awareness. Once we know what good behavior looks like and how to protect it, we can make the smart decisions about models, costs, and performance. And the chat playground here isn't just for experimentation. It's where AI agents earn the right to go into production. So great AI systems aren't defined by the biggest models. They're defined by the right ones. I hope you enjoyed this one and see you around in the next. Thank you. This is where your AI agent moves from good responses to truly optimized performance. In this exercise, you'll step into the role of refining a real agent by analyzing quality issues and improving it with modern fine-tuning techniques. You'll explore multiple optimization strategies, supervised fine-tuning, reinforcement fine-tuning, and direct preference optimization, and see how each approach can improve how an agent behaves in realistic scenarios. By the end of the activity, you'll understand how teams systematically diagnose weakness in AI responses and apply targeted training strategies to produce agents that are more accurate, reliable, and aligned with human expectations. You've now seen how optimization turns an AI agent from good enough into a system that consistently delivers real value in production. By choosing the right optimization strategy, whether it's supervised fine-tuning, reinforcement fine-tuning, or preference-based learning, along with high-quality data, thoughtful hyperparameter tuning, and deliberate model selection, teams can precisely target the behaviors that matter most. This is where monitoring, evaluation, and training come together. Insights from real usage, uniform measurable inputs and improvements, and each iteration makes the agent more accurate, efficient, and aligned with human expectations. With these Gen AI Ops optimization practices in place, your AI agents don't just respond, they evolve, adapt, and improve continuously as part of a mature, production-ready system. Over this learning journey, you've seen what it takes to move generative AI from experimentation into an engineered production-ready system. You explored how to automate AI evaluations with Microsoft Foundry and GitHub Actions, instrument agents with monitoring and observability, and continually improve responses through structured fine-tuning and optimization. The real message of this learning path is simple. Successful AI agents aren't static. They evolve through the disciplined evaluation, visibility, and iteration. When you combine automated evaluation pipelines, strong telemetry, and thoughtful tuning strategies, you create AI systems that aren't just impressive demos, but trustworthy, measurable, and continuously improving solutions in the real world. Thanks for being part of this journey. If what you've learned about AI-300 and Gen AI Ops spark new ideas, Don't stop here. Continue building your skills with hands-on labs and guided learning on Microsoft Learn at aka.ms/learn and explore the AI Skills Navigator to discover pathways tailored to your role, your interests, and what you want to do next in AI. Keep experimenting, keep building, and keep seeing what's possible. Congratulations on completing the AI-300 Azure AI Engineer Associate Learning Journey. Throughout this course, you explored the full life cycle of building modern AI solutions, learning how to design machine learning training solutions, run and optimize experiments in Azure Machine Learning, operationalize models with MLOps pipelines in GitHub, and build, evaluate, and improve AI agents using Microsoft Foundry. The key takeaway from AI-300 is that successful AI systems aren't just created, they're engineered, monitored, and continually improved. By applying structured experimentation, automated training and evaluation, and disciplined operation practices, you're prepared to move beyond prototypes and deliver scalable, trustworthy AI solutions in production. I want to encourage you to stay curious and continue exploring new capabilities. That's how you'll keep staying relevant. There are many ways to continue your learning journey. I invite you to search for the next favorite topic on Microsoft Learn at aka.ms/learn.